Welcome back. We are in the heart of trig identities, and today we're going to look at some specific trig identities called the sum and difference formulas. Now these formulas are the basis for several other identities, and they are formulas that if you are going to go on to calculus, you will be needing to know these like just off the top of your head to do problems. You're going to be having to do a lot of problems where you manipulate things and use these formulas. So I wanted to first derive the formulas and then show you some ways we might use them, like with numbers and so forth, like numerical problems. And also we'll do a little bit of a verifying identity using some of the formulas too. Okay, so to first step you through the formulas here and how they are derived, we are going to look at 2 points on a circle. We're going to call these 2 points P and Q. And what we're going to do is we're going to figure out what's going on as far as the distance between those 2 points. Like, so if you go, between P and Q, what's that distance there? So we're going to use a distance formula to help us with this. But first, let's do some labeling. Okay, the angles, this angle here, we're going to label as alpha. This angle here, we're going to label as beta. So then this angle is alpha take away beta. Because you have alpha and then you take away this beta part and that gives you this leftover right here. Okay, so then point P is the same thing as cosine beta, because we're on a unit circle, so cosine beta comma sine beta, because you've got the angle here is beta, and that point, it's cosine of the angle is the x-coordinate, sine is the y-coordinate, because we're on the unit circle. Then Q is cosine of alpha comma sine of alpha, because alpha is this angle. And so cosine of that is the x-coordinate, and the sine of that would be the y-coordinate. Okay, so then to do the distance between those 2 points, we're going to do this. Remember, the distance formula is the square root of the difference in the x's squared plus the difference in the y's squared. And this was derived using the Pythagorean theorem. Okay, so in our case, the distance is the square root of, well, x2 would be cosine alpha, x1 would be cosine beta. So cosine alpha minus cosine beta squared plus y2 minus y1, we got sine alpha minus sine beta squared. Okay, let me go and scroll on down so we can work that out some. Go ahead and do your squaring. You're going to end up, basically, cosine alpha minus cosine beta times itself, you're going to end up with cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. And then plus, you got sine alpha minus sine beta, you're going to get sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. Okay, all that's underneath the square root sign. So if you go through and do a little simplifying, cosine squared alpha plus sine squared alpha right here, that equals 1. Cosine squared beta plus sine squared beta equals 1. So you have 1 plus 1, which is 2, and then you have the minus 2 cosine alpha cosine beta and the minus 2 sine alpha sine beta. And that's as far as we can take that right now. But you're wondering, okay, what the heck does this have to do with anything? Well, let's go back up here. And let's take this angle, this alpha minus beta, and let's rotate it. And put it like this. So that this angle is still alpha minus beta. But we've rotated it in such a way that point P now is at 1, 0. And point Q now is at cosine alpha minus beta, comma, sine alpha minus beta. Because the angle here is alpha minus beta. And let's recompute that distance between P and Q using those coordinates. The distance is equal. It's the same angle measure, same distance between P and Q. The only difference is we rotated, so they're situated in a different place on the unit circle. So let's go through and work out all the distance stuff again, this time with that information. I won't rewrite the formula because you have the formula right there. This time we have cosine alpha minus beta minus 1 quantity squared plus sine alpha minus beta minus 0 quantity squared underneath that square root sign. So we do a little working out. Okay, do the squaring here. You get cosine squared alpha minus beta minus 2 cosine of alpha minus beta plus 1 plus sine squared alpha minus beta. And then you get that minus 0, so you get minus 0, you get zeros from there on doing that. Okay, so the sine squared alpha minus beta plus cosine squared alpha minus beta, that equals 1. So then we've got d equals square root. This one plus that one is 2. 2 minus 2 cosine of alpha minus beta. Now remember, though, that distance is the same either way, on either side, on the left side and on the right side. This distance between P and Q is the same. So we just shifted everything. So what we can do now is take this side and set it equal to that side. Take square root of 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. Set that equal to square root 2 minus 2 cosine of alpha minus beta. Well, if we go ahead and square both sides, that's going to get the root of the square roots for us. And if we go ahead and divide both sides by 2, then we end up with this. 1 minus cosine alpha cosine beta minus sine alpha sine beta equals 1 minus cosine of alpha minus beta. Subtract 1 from both sides and divide both sides by -1. You end up with cosine alpha cosine beta plus sine alpha sine beta equals cosine of alpha minus beta. And there, my friends, is one of your first sum and difference identities. The cosine of alpha minus beta equals cosine alpha, cosine beta, plus sine alpha, sine beta. You want to commit that to memory. You want to know this one because it will come up over and over again now, and if you continue in math like to calculus, it'll come up a lot in there too. But there's the first of your sum and difference identities. You got 5 more to go, but at least this is a start. Now if you're curious about cosine of alpha plus beta, keep in mind that you can write alpha plus beta as alpha minus negative beta. And then use your identity here. Cosine alpha, cosine of negative beta, plus sine alpha, sine of negative beta, and then work that out. So you get cosine of alpha plus beta equals cosine alpha. Cosine negative beta is the same thing as cosine beta. You guys learned that a little while ago. You know, cosine's an even function. Cosine of a negative equals just cosine of the positive. But sine, being an odd function, sine of negative beta equals negative sine beta. So this is going to be a minus sine alpha sine beta. And there's your second of your sum and difference identities. Another one to commit to memory. Now I'll let you on a little secret of how I remember these two. I've got cosine, cosine, sine, sine. Cosine I think of close. Like when you're doing cosine on a triangle, it's an adjacent side over hypotenuse. It's the closer side over the hypotenuse. Well here, cosines stay close together, sines stay close together. But to make up for being close together, the SIGN is opposite. So if you're doing the cosine of a difference, this will be a plus. If you're doing cosine of a plus, this will be a minus. But that's the price they pay for staying close together, for cosines sticking together and sines sticking together. That's how I remember it, but you have to come up with your own way. Okay, so how could this be useful? Well, you might have some problems where you might need to find exact values of something, but you're looking at it and going, well, that's not on my unit circle, so how could I rewrite it? How could I make this work for me? For example, you might have something like find the cosine of negative 75 degrees. And you're sitting there going, okay, negative 75, I know that's the clockwise direction. That's 15 degrees short of hitting the 90 degree mark. But that's not going to help me when I'm using my unit circle. Like, it's not a nice, pretty number. So, what can I do with this? Well, you can say, you know what? I can rewrite negative 75 degrees as 150 degrees minus 225 degrees. Because 150 degrees is on the unit circle, and so is 225. So this can be very handy. So you can then go, okay, using my identity I now know, I can rewrite that as cosine of 150 degrees, cosine of 225 degrees. And since the cosines stay close, the price we pay is to change the SIGN to plus sine of 150, sine of 225. All of these are on the unit circle, making this easier to work. I've got negative square root of 3 over 2 times negative square root of 2 over 2 plus 1/2 times negative square root of 2 over 2. So we got what? Square root of 6 over 4 minus square root of 2 over 4. And then that could be rewritten square root of 6 minus square root of 2 all over 4. Leave it in exact form that way. And now I found the cosine of negative 75 degrees. So I took something that wasn't on my unit circle and I applied an identity and was able to turn it into a problem where the unit circle could come into handy. Isn't that cool? Right? Not only can you break it up, but sometimes you might be given a problem where you have to put it together. You might be given cosine of 173 degrees, cosine of 83 degrees, plus sine of 173 degrees, sine of 83 degrees. You might go, oh man, 173 and 83, those aren't on my unit circle. But wait a minute. If I look at this a little more closely, it looks a heck of a lot like one of my identities. In fact, it looks like the cosine of a difference. Cosine, cosine plus sine, sine. So that's the same thing as cosine of these two angles subtracted. Ooh, this might be doable. 173 minus 83 is 90. Cosine of 90? Oh, I can do that. I get 0. Not bad, eh? All right. So that gives you something to work with. Okay. So now knowing that, having that little discovery, let's move on and start seeing what some of the other sum and difference identities are. You know, we can't stop with cosine. We got to explore sines and tangents too. So let's go there. All right, before we explore sine though, let's do something real quick here. Let's uncover one of the cofunction identities. If we take cosine of 90 degrees minus theta, we can apply our identity and say that's cosine of 90 degrees cosine theta plus sine of 90 degrees sine of theta. Okay, so cosine of 90 degrees we know is 0. Sine of 90 degrees we know is 1. So it turns out cosine of 90 degrees minus theta equals sine of theta. Is that cool or what? All right, let's use that to help us to derive situations with sines. Let's take, let's try to derive sine here. Let's say we have something like sine of alpha plus beta. So we want to, instead of doing cosine of a sum, we're doing sine of a sum. But we know that the sine of our angle equals the cosine of 90 degrees minus that angle. So this is equals to cosine of 90 degrees minus the alpha plus beta. Well, let's rewrite that a little bit to be cosine of 90 degrees minus alpha and then minus beta. Because we had the 90 degrees minus theta up here. That was 90 degrees minus alpha. Let's play with that. All right, we got cosine of a difference, so we can rewrite that as cosine of 90 degrees minus alpha, cosine of beta, then pay the price to keep close together, change minus to plus, sine of 90 degrees minus alpha, sine of beta. All right. Cosine of 90 degrees minus alpha we know is actually sine. So sine of alpha, cosine beta, plus, all right, the sine beta is going to stay, but what the heck is this sine of 90 degrees minus alpha? Well, sine and cosine, remember how when we were doing the graphing back in the last unit, how you could take the sine graph and shift it pi over 2 units and it would match up with cosine. Same thing vice versa, cosine, shift it, negative pi over 2, you get sine. Well, pi over 2 or 90 degrees. it turns out, just like cosine of 90 minus theta equals sine of theta, you also have that sine of 90 degrees minus theta equals cosine theta. So, this equals cosine of alpha right here. There's another one of our identities. Woohoo! Okay, let's box that one in. And then to get the sign of the difference, just like with cosine, we just treat it like this. Sine of alpha plus negative beta. Treat it like that. So then you got sine alpha cosine negative beta plus cosine alpha sine of negative beta. So sine of alpha minus beta, sine alpha, cosine of negative beta is the same thing as cosine beta. Then over here, sine of negative beta is the same thing as minus sine of beta. So we'll change that plus to a minus. And you know what? Let me rearrange the order a little bit. Let's write the sine of beta first, cosine alpha. I just want to do that. It doesn't matter, but I wanted to do that to show you. On this one, on sines, sine of a sum, sine of a difference. I remember this because sine, like cosine, they stayed close together. So sine, they're going to separate. You have sine and cosine together here, cosine, sine together there. Same thing here. But the trade-off is that you have the same SIG in. So the plus is in plus, you got minus, you got minus. But there's some of your, two more of your identities. Yay! Nice, right? Okay, so let's look at a couple of examples with the sines, or an example. Let's say you have to do sine of negative 15 degrees. Well, now, before you couldn't do that on your circle, but now you can rewrite negative 15 degrees as 30 degrees minus 45 degrees and work with that. Because now you know that this is the same thing as sine of 30 degrees, cosine of 45, and then we get to keep the minus, cosine of the 30 degrees, sine of the 45. Woohoo! So we got 1/2 times square root of 2 over 2 minus square root of 3 over 2 times square root of 2 over 2. So we got square root of 2 over 4 minus square root of 6 over 4. So clean that up. Square root of 2 minus square root of 6 all over 4. So something you previously couldn't do because of limitations with your unit circle, now you can. Pretty neat, right? Okay, let's develop the tangent. Tangent of alpha plus beta. Well, tangent's the sine over cosine. So we could do sine of alpha plus beta over cosine of alpha plus beta. Now we've got identities for those. So we got what? Sine alpha cosine beta plus cosine alpha sine beta over cosine alpha cosine beta minus sine alpha sine beta. Alright, looks a little hard to work with, but cool little thing we can do here. We can multiply top and bottom by 1 over cosine alpha cosine beta. And this will give us a very interesting result. Because, tangent is sine over cosine. So the point of doing this is to try to get sine over cosine along the way. And that will get us into terms of tangents, because we want to try to work with, if we know tangent alpha, tangent beta, we want to be able to work with those in this identity. So by multiplying by this, we'll end up with some sines over cosines. Let's see, up top we have the sine alpha cosine beta over cosine alpha cosine beta, plus we're going to have the cosine alpha cosine beta, or sine beta over cosine alpha cosine beta. That's just the numerator. And then denominator, we got cosine alpha cosine beta over cosine alpha cosine beta. You can start seeing where things are going to reduce really nicely. Minus sine alpha sine beta over cosine alpha cosine beta. It all falls into place now. Tangent of alpha plus beta is going to equal, well, in this one, cosine beta over cosine beta is 1. Sine alpha over cosine alpha is tangent alpha. Plus cosine alpha over cosine alpha is 1. Sine beta over cosine beta is tan beta. Woo. On the bottom, these reduce to 1. So does this. So we got 1 minus, let's see here, what do we got? Sine alpha over cosine alpha is tan alpha. Sine beta over cosine beta is tan beta. And there we go. Yippity skippity. There it is. And then, as we did before, if you want to do alpha minus beta, think about it as being like alpha plus negative beta. So we're going to have tan alpha plus tan of negative beta all over 1 minus tan alpha tan negative beta. Well, our tans are odd functions. So tan of negative beta is the same thing as negative tan beta. And here again, tan negative beta is the same thing as negative tan beta, so that minus is going to turn into a plus tan alpha tan beta. So there's the difference version of it. Pretty nice, right? Alright, let's look at an example where we'll work with that and use it. Okay, let's say you have something like the tan of 13 pi over 12. Well, on our unit circle, we have denominators of 3, 4, and 6. I guess I could do this with a pi plus pi over 6, right? No, I couldn't. No, it'd have to be pi plus pi over 12. Pi plus pi over 12. 12 pi over 12 plus pi over 12. But pi over 12 I don't have on my unit circle. I don't want to do that. If I use denominators of 3 and 4, I can make this work. Let's see here. Let's say I use 3 pi over 4 and pi over 3. That should work, because really I've got 9 pi over 12 plus 4 pi over 12. Yeah, and that's 13 pi over 12. Alright, good. And those are on my unit circle. So then I could say, using my identity, tan of 3 pi over 4 plus tan of pi over 3. And the whole thing over 1 minus tan of 3 pi over 4, tan of pi over 3. So that equals, let's see, tan of 3 pi over 4 is what? Negative 1. Plus tan of pi over 3 is square root of 3. All over 1 minus negative 1 times square root of 3. So I get negative 1 plus square root of 3 over positive 1 plus square root of 3. If I rationalize the denominator, I take the conjugate of the denominator there and multiply top and bottom by it. I'm going to end up with negative 1 plus square root of 3 plus square root of 3 minus 3 over 1 minus 3. So I'm going to end up with negative 4 plus 2 square roots of 3 over negative 2, or 2 minus the square root of 3. And now I did a problem I wasn't previously able to do using my unit circle. Woo-hoo! Very nice. Okay. Alright, let's revisit one other topic real quickly before we do one final thing. Earlier I introduced to you two of the cofunction identities. Identities. There we go. I introduced two of those to you. I introduced cosine of 90 degrees minus theta equals sine of theta. We used the cosine of a difference formula to prove that. And then, you know, sine is related to cosine by being, you know, the shift pi over 2. So this cofunction identity is true as well. And if, you know, if this is true for cosine and sine, this is also going to be true for their reciprocals. So you can say secant of 90 degrees minus theta equals cosecant theta. You can also say cosecant of 90 degrees minus theta equals secant theta. Turns out too, though, if you do tangent of 90 degrees minus theta, go ahead and use the tangent formula we just learned, just derived, and that will work out to cotangent theta. But then its reciprocal cotangent, you can work it as well. And that's tangent. So just some relationships that are good to remember. They might come in useful. Like you might be asked something such as, find the smallest positive theta that makes this true. Secant theta equals cosecant of 62 degrees. Well, if you know that secant of 90 minus theta equals cosecant of theta, then you can say, well, the secant of 90 degrees minus 62 degrees equals cosecant of 62 degrees. So then you can say secant of 28 degrees. Same thing as cosecant of 62 degrees. So these two angles are going to add up to 90 degrees. If they give it to you in radians, then you're dealing with, instead of 90 degrees, you're dealing with pi over 2. Something like that. But now you can work on those cofunction identities if they pop up, if you're asked to do something with those. Okay, one more problem I want to work. I'm just going to scoot down on this piece here. It's a verifying identity. But it's going to use some of this information we just learned. there's the problem, is that we're asked to verify this identity. Now to me, the left side looks more complicated, and that's the side where I'm like, oh, I recognize these identities we were just doing, so let me work with that. I have tangent of a sum, tangent of pi over 4 plus t, so let me rewrite that. Tan pi over 4 plus tan t over 1 minus tan pi over 4 tan t plus, and then this one's a tangent of a difference, so I got tan pi over 4 minus tan t over 1 plus tan pi over 4 tan t. Well, tan of pi over 4 is 1, because at pi over 4, your sine is square root of 2 over 2, your cosine is square root of 2 over 2. So when you put square root of 2 over itself, you're going to get 1. So you get 1 plus tan t over 1 minus tan t plus 1 minus tan t over 1 plus tan t. So these fractions are starting to get a little simpler. So then I'm going to get a common denominator. Multiply top and bottom here by 1 plus tan t. And multiply top and bottom there by 1 minus tan t. So the denominators are common now. They're going to be 1 minus tan t, 1 plus tan t. Alright. So work with that a little. Square up top. You get 1 plus 2 tan t plus tan squared t plus 1 minus 2 tan t plus tan squared t all over 1 minus tan squared t. Okay, 2 tan t and minus 2 tan t are gone. So I got 2 plus 2 tan squared t up in the numerator. And I got 1 minus tan squared t in the denominator. Up top I can factor out a 2. Don't really have anything I can factor in the denominator. But it turns out 1 plus tan squared t I know from past identities to be secant squared t. Whoa! Check that out. In the original problem, we were trying to verify that it equaled 2 secant squared t over 1 minus tan squared t. And there we are. We did it! Woohoo! And we were using tangent of a sum, tangent of a difference. Use those identities to help us to verify that new identity problem. And once you verify an identity, you can use it from then on for other problems. So that's really cool about it too. Okay, so that's enough about sum and difference for today. We still have to move forward, and next we'll talk about the double angle and half angle, but those identities come from sum and difference. So you're going to see how this progression, how everything builds on itself. But for now, thank you for joining us, and I look forward to seeing you again soon.